Welcome to the lesson on conditional probability. Conditional probability is a model for chance behavior. Let's take flipping a coin as an example. Coin tossing has two parts: a list of possible outcomes, which in this case would be heads or tails, and a probability for each outcome. Then we have sample space. Sample space is a set of all possible outcomes. And we can write that as, actually it's right down here, sample space would look like that. Okay, the probability model is a description of some chance process that consists of two parts, the sample space and the probability for each outcome. Alright, we have events in probability, and an event is any collection of outcomes from some chance process. And those are denoted by capital letters. Designated by capital letters. Again, Arthur has joined us for another video, so he is in the background, and I do apologize for his whining and crying. Alright, there are some basic rules for probability. The probability of any event is a number between 0 and 1. An event with a probability of 0 never occurs. An event with a probability of 1 occurs on every trial. An event with a probability of 0.5 occurs in half the trials. All possible outcomes together must have probabilities whose sum is 1. Cut off a little bit. And if all outcomes are equally likely, we can use the probability formula, which is the probability of some event, we'll call that event A, is equal to the number of outcomes of A divided by the total number of outcomes in sample space. Okay, the probability that an event does not occur is 1 minus the probability that the event does occur. Let's say that the probability of an event A occurring is 70%. And we want to find the probability that this event does not occur. So, the probability of A not occurring is 1.00 minus 70%, we'll change it to a decimal, 0.7, and that is equal to 0.3. So the complement, this is called the complement of A, when we find out when A does not occur. So the complement of A, which is denoted by A to the superscript C, is going to be equal to, in this case, to 30%. If two events have no outcomes in common, the probability that the one or the other occurs is the sum of their individual probabilities. So let's say that the probability of event A occurring is 40%, and the probability that another event occurs, let's call that the probability of B, is 25%. And the two can never occur together, then one or the other occurs 40 plus 25, 65% of the time. Again, these two events cannot occur at the same time, and one or the other will occur 65% of the time. Mutually exclusive or disjoint is when two events have no outcomes in common, meaning they can never occur together. Alright, in event A will be between, the probability of event A will fall between 0 and 1. Sample space is always has to be equal to 1. The complement rule is the probability, the complement of A is equal to 1 minus the probability of A. And the addition rule. And this only works when two events are mutually exclusive, meaning they can never occur at the same time. And that will be the probability of A or B is equal to the probability of A plus the probability of B. When we find the probability of two events, it helps to use a two-way table or a Venn diagram. So I'm going to go ahead and display a Venn diagram for you of two events A and B. And let's go ahead and make a box. And event A we'll do in blue. And event B I'll do in another color, let's do yellow. Alright, where they overlap is when both events occur. Okay. So the outcomes here. Outcomes are double counted where they overlap. By probability of A and plus the probability of B. So this space is the probability of A. This space is the probability of B. And the center is probability of A and B. Okay, we're going to have to deal with what's called a double counting problem when we're finding the probability of one event or another event occurring. So, double counting problem. Okay, so let's say we want to find the probability of A or B occurring. We can do this by finding the probability of A plus the probability of B, and where they overlap we have to subtract, so that would be minus the probability of A and B. Alright, now I'm going to show you some visuals for some of our vocabulary that we've had, complement, mutually exclusive, and also how to write particular probabilities with probability notation. Let me switch colors here. We'll use Venn diagrams, nice visuals. And we've got this event A occurring. And the complement of A would be A superscript C and on the outside. And then let's do mutually exclusive, a nice visual for mutually exclusive. Would be where two events never occur at the same time. So I have event A, which does not overlap with event B, making them mutually exclusive because they can never occur at the same time, hence the not overlapping. Alright, sorry about my handwriting there. Switch colors again. And let's do some probability notation. When I'm looking for the probability of A and the probability of B, which is where they overlap, we can write that with probability notation, and it looks like this: A and B. And then one last, when we want to find the probability of A or B occurring. And that would be all of this. And that would be A unioned with B, or A or B. Okay, we're going to move on to conditional probability, not property, and independence. And okay, a study was conducted on pure steers and whether males and females had pure steers. So I'm going to make a two-way table. Gender, yes, no, and total. My genders are male, female. Okay, and my totals. All right, switch colors here. Okay, the number of males that said yes to having their ears pierced was 19. Number said no were 71, for a total of 90, marginal total of 90. And the number of females that said yes to having their ears pierced is 84. No is 4, for a marginal total of 88. And then the total number that said yes was 103. Total number that said no, 75, for a grand total of 178. So now we're going to go ahead and find some probabilities. We're going to say that the event A is male, and event B will be pierced ears. Okay, and we're going to find the probability of A will be the probability of males, which is, go up here, we got 90 males out of a grand total of 178. And let's do the probability of B, which will be the probability of ears pierced. So I'll go up to the total number of people that got their ears pierced, which is 103, over the grand total of 178. That's the probability of having your ears pierced. Switch up the colors. Let's find the probability of A and B, which will be the probability of being male and having pierced ears. So the males that have pierced ears are 19 out of our grand total of 178. Now I want to find the probability of A or B. Remember that's the U, which will equal probabilities of male or pierced ears. So I've got 174 out of 178. So I add my total of males with my total of pierced ears, and I have 174 out of my grand total of 178. Okay, we have to go over how we got 174 to 78. Remember, these overlap. These can occur. They're not mutually exclusive. So we're going to have to use the probability of A or B to be equal to the probability of A plus the probability of B minus the probability of A and B. What does that look like? Well, the probability of A, we already found, is 90 out of 178. Plus the probability of B is 103 out of 178. Minus the probability of A and B, which we found to be 19 out of 178. We get 40 plus 100, or 90 plus 103 is 193 minus 19 will be equal to 174 out of 178. Conditional probability is when we are trying to find the probability that one event will happen under the condition that some other event has already happened. The phrase "given that" signals that there's a condition. So let's say that P is male and has pierced ears, given that he has pierced ears. So that would look like this. P is male, given he has pierced ears. And that, remember, this line right here means given that. All right. So the probability of A given B, which is male, given that they have pierced ears, would be equal to 19 over 103. And the probability of B given A would be equal to 19 over 90. Why difference between these two? Okay, the probability of it being male given that they have pierced ears, meaning the condition is yes to pierced ears. So if we look back at our two-way table, yes to pierced ears has a grand total of 103. And given that they're male, males are 19. So, I mean, males given that they have pierced ears. Males is 19. Given that they have pierced ears, that's 103 for the total. And then given that they have having pierced ears, given that they're male, so we go to the male column, which has a grand total of 90. And the total for pierced ears would be 19. So that's the difference between the wording in those conditions and how the conditions change between given that pierced ears or given that they're male. All right, independent events. Independent events are when you know one event has happened and it does not change the likelihood that another event will happen. Okay, let's move on to tree diagrams. They are a good way to model chance behavior. So we'll go back to the coin, toss of a coin. Two things can happen when we toss a coin. One of them, it lands on heads. The other, it lands on tails. And then if we toss a coin again, we have another two possible outcomes. Heads or tails. And heads or tails. The chance on the first toss that it lands on heads is 1/2. Chance of tails, 1/2. And then we go from tails here again, 1/2. And 1/2 on the second toss of the coin. Alright. So the probability of tossing a coin twice and getting two heads is equal to 1/2 times 1/2, which is 1/4. Alright, multiplying along the branches in a tree diagram leads to the method of finding the probability of A and B. So let's do probability of A and B, that these two events will happen together. So the probability of both A and B occurring is equal to the probability of A times the probability of B. Now, independence has a special multiplication rule. If two events are independent, probability of B given A equals the probability of B, then they're independent. The probability of A and B is equal to the probability of A times the probability of B given A, which equals the probability of A times the probability of B. All right, two mutually exclusive events can never be independent because if one event happens, the other event is guaranteed not to happen. Moving on to conditional probability formula. When we need to find conditional probabilities, we can use the formula. Let's say P, oops, my pen working here. Probability of B, given that A has already happened, is equal to the probability of A and B, or that looks like that, divided by the probability of A. Thank you for joining me in the lesson, Conditional Probability.